Hello and welcome to the first lecture for Chemistry for Living Systems. Now, what you're watching right now, is an online resource to help you revise some of the topics that we cover in class. This is not intended to be a replacement for attending class, okay? So make sure that you attend the lectures. I know they're at perhaps an inconvenient time for some people, but do your best to attend. And occasionally, you'll also have some online resources such as this to help you along as well. Now, this isn't going to be the complete lecture. In fact, none of these little online resources are going to be a complete lecture because that's just a little bit tedious to have to sit through a complete lecture. So what they're intended to be are shorter parts of the lecture, okay, so you can revise important topics, but they are not a replacement for attending class, okay? You need to make sure that you're still coming along, and there's often going to be some important information as well that might be covered in class that isn't covered as part of these extra help online resources. Okay, so today we're going to get started on chemical foundations. Okay, so the first lecture was on the topic of chemical foundations as well as basic mathematics as well. So I won't be covering basic mathematics in this particular file, okay? So let's get started. Okay, welcome to the course. If this is the first time you've heard my voice or the first time that you've entered any of the course material, welcome. I hope you enjoy the course. I think it's a fun course. Okay, the first week, maybe even the first week or two, can be a little bit tedious, especially if you've done chemistry before. If you haven't ever done any chemistry before, or it's been a long time, this is going to be very valuable to you to go through this revision. Otherwise, I hope that you enjoy the course and you find these resources helpful as you go through. Let's begin by discussing the scientific method. Okay, we know that science is the framework for gaining and organising knowledge, but we need to have a look at how does the scientific method work, and here's 4 steps that we'll go through as an example to show how the scientific method works. Let's discuss the scientific method. Okay, how does the scientific method work? We begin by making an observation. So observations may be qualitative. So for example, coffee tends to stain if it is spilt, or they can be quantitative. So for example, water boils at 100 degrees, or my chemistry book weighs 2 kilograms. So quantitative observations involve numbers and units, and qualitative observations don't. So this is a quick way to tell whether you've got a qualitative or a quantitative observation. So step 2 is to formulate a hypothesis. So a hypothesis is a possible explanation for an observation. So for example, the coffee stains because of the sugar content. Okay, so the observation was coffee tends to stain as it is spilled, and the hypothesis might be that the coffee stains because of the sugar content. Now the hypothesis doesn't have to be the correct answer. Okay, it doesn't have to be the correct explanation. It's just a possible explanation for an observation. And with every hypothesis, there will be a null hypothesis. So this is where we design our experiments. Okay, so basically, a null hypothesis is the opposite of our hypothesis. So our null hypothesis in this case will be the sugar in the coffee is not responsible for the stain. Now, this is really important because you need to check your data and check your statistics after you perform the experiment to make sure that you're not just seeing the result that you want to see, okay? And this is really important. When you enter a scientific experiment, you need to be aware of the theory behind it, and you're probably going into it with an idea of what you want to see happening, but you need to make sure that you're not seeing a relationship that isn't really there. Okay, so you need the data to back this up. Then you perform your experiments. So you've got your hypothesis, you've got your null hypothesis, you perform your experiments, so you're testing the hypothesis, okay? And through the experiments, you're going to see new observations, and this will bring the process back to the beginning again. So you're going to find new observations as you go along. Right, so I've also covering the topic here of a natural law. Down the bottom of the slide there, you can see a natural law is a summary of the observed behaviour. So for example, we've got the law of conservation of mass. So it's not really something that's often disputed, okay? Whereas a theory, it's an explanation of a behaviour, okay? So we know that, say, atoms behave in a certain way or molecules behave in a certain way. So in atomic theory, or we've got valence shell electron pair repulsion theory, where we know that we've got a certain behaviour. Okay, so we use a theory to explain this behaviour. Now, the theory isn't necessarily going to be the complete explanation of why it occurs, but it does give us a way of predicting what will happen in the model. Okay, so the theory, based on the theory, we predict the model will have this behaviour, and it does. It doesn't prove that the theory is correct, it just shows that the theory works. And the theories can change over time. So, and you'll see next week when we're covering atomic theory, that atomic theory throughout history has changed over time. It's going to be improved as we go along. Okay, now let's have a look at units. So I'm sure you've heard of units before. Okay, so for example, here we have the fundamental SI units. Now, SI units stands for the International System of Units. It is French, so it's actually System International of units that we use in science around the world. And here are some physical quantities. So we've got mass, length, time, temperature, electric current, amount of substance, luminous intensity, and volume. And you can see each of these has a corresponding unit that we use. So the kilogram, the meter, the second, the Kelvin, the ampere, the mole, the candela, and the litre. Now notice that there's the odd one out, and the odd one out there is the kilogram, because we're using that prefix, okay? We're using kilo, and kilo means 1,000. So the SI unit for mass isn't the gram, it's actually the kilogram, okay? And this is probably more important, perhaps more so in physics, whereas in chemistry we generally do use grams for our calculations, okay? And as long as you stick with the same unit through the calculation, you'll always be able to work out what your answer will be, what unit to use for your answer, okay? So any measurement or any quantitative observation must always consist of two parts. So you've got your number and you've got a scale, okay? You need both of these parts to be present for the measurement to be meaningful. Okay, so I can't just say, well, how much water do we have in this glass? Okay, there's 260 water in this glass. You need a unit to go along with that as well. You need to say there's 260 millilitres. Okay, you need to make sure that you've got a measurement as well as having the units. Okay, so just make sure that you write your units down whenever you're giving an answer for a question as well to get your full marks. Okay. Now, the International System of Units has been used since 1960. Okay, it's been used for quite a long time, and in Australia, at least, we finished this up in the 1980s, completely converting over to the metric system. Okay, using the SI units in Australia. So I think most people from Australia are quite familiar with SI units, but it's something to be aware of as we go through the course. All right. So I mentioned unit prefixes on the previous slide when we were looking at the kilogram. So there's different prefixes that we'll use as well as we go through. So because the fundamental units are not always convenient, okay, so you're not going to express the mass of a pin in kilograms, for example, we need to use prefixes to change the size of the unit. Okay, and this is something that you might like to commit to memory. So you're not going to get a guide for how to do these conversions in an exam situation. Okay, so the important ones though that we've got here would be more We probably won't use deci very often. Centi, milli, micro, and nano are quite important. Okay, dec is fairly rare, hecto is fairly rare, but kilo and mega are also important as well. Okay, so there's a small handful of important ones there to remember. So those ones again, kilo, okay, mega as well, also centi, milli, micro, nano. Knowing that a nanogram is smaller than a microgram is important, and you'll notice that they actually go in groups of 1,000. Okay, so moving from the base unit to say a milligram, we know that that's say 1,000th of a gram is a milligram, and 1,000th of a milligram is a microgram, and 1,000th of a microgram is a nanogram. So just notice those groups of 1,000, and they're the important ones. Okay, so something like centi, most people understand that centi is 100 or 100th, okay, of a unit. So there's 100 centimeters in a meter. This is something that most people, I think, remember. But the important ones, and you can see at the bottom of the slide there, we've got multiply by 1,000 to convert from a kilogram to a gram. There's 1,000 grams in a kilogram. Multiply by 1,000 to convert a gram into a milligram, and so on. So for the most part, when you're converting between units, you'll be multiplying or dividing by 1,000 to perform the task. Okay, so those other ones perhaps aren't so important. And you can see that we can express these in scientific notation down there on the right hand side. Don't worry if it's been a while since you've done scientific notation, we're going to cover that in this lecture as well. Alright, let's have a look at a practice question. Unit conversion. How would you convert 0.001 grams into milligrams? Well, I'll show you two methods. You might even have your own method that you use. Okay, you don't have to use one of the methods that we discussed in the lecture. So here's some examples of how you might like to do it. And chances are, in a tutorial, your tutor might use a completely different method to this. Okay, it just depends on where your personal preference is. Okay, so I'm not going to make you use a particular method, but you might like to use one of these. So method one, you could use a conversion factor. Okay, so if we're going to convert 0.001 grams into milligrams, we could use a conversion factor. So step one, what are the possible conversion factors? Okay, so either we're going to use, there's 1,000 milligrams in a gram, so 1,000 divided by 1, or it's going to be there's 1 gram per 1,000 milligrams, 1 over 1,000. And which one to select depends on which units you want to end up with. Okay, so you choose the one that has those units on the numerator. So you can see here, we've got the option of having milligrams on the numerator. So remember, whenever you've got a fraction, the numerator's on the top and the denominator's on the bottom. So the milligrams on the numerator, that means our answer will have milligrams as its unit. Okay, so milligrams on the numerator, so our answer will have milligrams as the unit. Or method two, you could use a cross multiplication technique, and this is where you can cross multiply. So I probably won't use this method, but if you set out a grid as shown here, you can say there's 1,000 milligrams in a gram. How many milligrams are in 0.001 grams? So if you multiply the blue squares and divide the answer by the top green square, that will give you the answer in milligrams. Okay, so there's another method that you might like to use. Let's have a look now at the difference between precision and accuracy. So a lot of times you'll hear that people actually use these two terms interchangeably. Okay, they're not interchangeable. There's a difference between precision and accuracy. So if something is precise, that means the measured values are close to each other, but not necessarily close to the true value. So that means if you've got an instrument that you're using in the lab that's very precise, that means you're going to be getting the same value over and over and over every time you make a measurement. But it may or may not be the true value because that device might be out of calibration. Okay, if something's very accurate, that means the measured values are very close to the true value. Okay, so if something's unprecise, that means that it has a lot of systematic error. If something's inaccurate, it might have random error. Okay, so depending on the instrumentation, there may be some error in there that's impossible to iron out. So we can't iron out those wrinkles. It's a very accurate instrument, but you know that you're going to have to take a handful of measurements and average those out to get a good result from that instrument, okay? And this is why in the lab we often make several measurements of the same thing. So this is checking the precision of the instrument, so that way we can make an average, okay? There's not too much that we can do about accuracy other than making sure that our instrumentation is in good calibration, and sometimes this is out of our control. You need to be aware as well of uncertainty in measurements that you're making. So whenever you make any sort of a measurement in the lab, there's a good chance that there's going to be some uncertainty. So this could be due to the way, in this case we're looking at glassware, so this could be due to the way the glassware has been manufactured. So on the left here you can see we have a beaker. It has calibrated measurements up the side, but you can see it's calibrated in 10 milliliter units. So that means we're not going to be able to measure very accurately, for example, 28 milliliters. So we know that the error is going to be in the unit place, and the uncertainty may be 28 plus or minus 1 milliliter, hypothetically, okay? We'll have a closer look at error later on in this lecture and how we can actually work with error mathematically. In reality, you'd find that on most glassware now, the error associated with the glassware is actually printed on the glassware as well, to let you know the manufacturing standards that have been used when the glassware was made. Okay, so this measuring cylinder in the middle is calibrated in 1 milliliter units. So, for example, if we were measuring 28.2 milliliters, the error would be in the tenths place. Now, see what we're doing here? We're actually estimating one more digit than we have in our calibrated units. So this measuring cylinder is in 1 milliliter units, but our measurement is 28.2 milliliters. Now this is standard practice to put that 0.2, to put that extra place, okay? So always estimate your last decimal place, for example, when you're using glassware. This is standard practice. And you know that there's going to be some error in there as well. So for example, our burette is calibrated in 0.1 milliliter units, and later in the semester you're actually going to be doing a titration using a burette, and it will be calibrated in 0.1 milliliter units. You need to make sure that you estimate that hundredths place. So in this case we're looking at 28.30 milliliters, and we know that we're going to have some error there in the hundredths place, some uncertainty, okay, I should say. We'll discuss error later on in the lecture anyway. Let's have a look at significant figures. So chances are you've seen this before, and if you haven't, don't worry. Okay, so some people may not have covered this before in previous studies. So whenever we make any kind of a measurement, it's not true that necessarily all of the figures are going to be significant. So consider, for example, if you're using two different balances in the same lab. So you might have a balance used to weigh out some substances. So one balance might be accurate to 5 decimal places, and another balance might be accurate to, say, 3 decimal places. Okay, if you use one balance early in the day and it's not available later in the day, so you use the other balance to measure out a substance later in the day, and you add the two numbers together, you need to consider that you can disregard the extra significant figures, or the extra figures that you were able to obtain with the more accurate scale. Okay, so you're going to need to cut those down. Your answer is going to need to be cut down to just 3 decimal places. And this is what we do when we add two numbers together. So we go to the least amount of decimal places. If you're multiplying two numbers together, then you go to the least amount of significant figures. And this is something that we'll work more on as we go through the tutorial questions. So that explains why we need significant figures, but how do we actually work with them? So when you're given a number, how do we show that we want some figures to be significant and others not to be significant? Because when you've taken a measurement, you can write down all of the figures that the device has given you, but we need to write them in a way so we know which of the figures are important and which ones aren't. Okay? Because typically what we'll do is we'll leave those so-called unimportant figures in, when we're performing mathematical calculations, but then at the end, when we give our answer, we'll take them out, only leaving the significant figures behind. So, given any number, okay, there is a set of rules to determine how many significant figures it has. So in this number that we've got here, for example, so we've got 0.003009,200. So you can see we've got a decimal place there, okay? And we've got a leading 0. So the 0 before the decimal place is not significant. That's cosmetic only, that 0. It's only there to show where the decimal place is, okay? If there was a digit before that, to the left of that, then that 0 would become significant. But in this case, because there's no figures to the left of that 0, it's a not significant 0. And the best way to learn these rules is by practicing examples, and we've got a lot of examples there for you in this week's tutorial that you can actually practice through. Okay. Now, the next two zeros there after the decimal place are not significant because they're placeholders. They show where the significant figures start. So the significant figures start there with the 3. Okay, so the 3 that's in the 1000th column. So moving on from that 3, the two zeros sandwiched in between are also significant. Okay, then our 9 and our 2 are significant, and our trailing zeros are also significant as well. So this is our trailing zeros rule, where any 0 that trails to the right hand side after a decimal place, after there have been non-zero numbers, are significant as well. And I know this sounds very confusing, and this example that you've been given is actually quite a tricky example, but if you start by practicing some of the simpler examples in the tutorial questions, you'll find that you get the hang of it very, very quickly. Okay, you get an ambiguous situation sometimes with a number like, say, 100. So if you're given a number 100 with no decimal places, then you can assume that it has most likely 3 significant figures, even though, following the rules, you could say that it has 1 significant figure. And in fact, if you follow the rules and get 1 significant figure, okay, if I asked you a question in an exam, okay, how many significant figures are there in the number 100, and you give me the answer 1, that is a correct answer. Just the 1 is significant. Okay, the two zeros are not significant. All right. We'll discuss this in greater detail later on, but for now, just be aware that there is a way to work out how many significant figures there are in any number that you're given, and by practicing the rules, you can very quickly learn how to do this, how to work these out. Okay, and we'll practice some of these in the tutorial. So when you're working with significant figures, when you're adding, subtracting, multiplying, dividing, you need to also work out how many significant figures there are in your answer. Okay, so in this first example here, we've got an addition. So we've got 12.11 plus 18.0. Okay, now we're looking and we're considering how many significant figures we have. Okay, so in this case, we can imagine that it's been stated in the question that yes, this 0 after the 18.0 is a significant figure. Okay, so we've got 12.11 and 18.0, so we've got 1 significant figure, 1 significant decimal place versus 2 decimal places. Okay, so when you're adding and subtracting, you go to the least number of decimal places. So in this case, you take your 12.11, add it to 18.0, and in your calculator or in your head, you get 30.11, but then you have to correct that to 1 decimal place. You go to the least number of decimal places if you're adding or subtracting. Now for multiplication or division, we have to go to the least number of significant figures. Okay, so in this example, we've got 4.56 multiplied by 1.4. So now we look at the 4.56, that's got 3 significant figures. 4.56, 3 significant figures. Okay, if we look at the 1.4, that has 2 significant figures. So that means our answer, our final answer, corrected answer, should have only 2 significant figures. So our calculator says, okay, it's 6.38, but we need to correct this and round it off to only 2 significant figures. So the 6.38 becomes a 6.4. Now that's the difference. Now try not to forget the difference between adding and subtracting, you go to the least number of decimal places, and multiplication and division, you go to the least number of significant figures. Okay, so that's the key difference between the two operations. Now, if you forget how to round off, I hope no one's forgotten how to round off, but hey, I better let you know anyway. So you need to round off. So for example, if you've got the number 1.33, it's going to round off to 1.3. So if it's less than 5, the preceding digit stays the same. Okay? If it's greater than 5, the preceding digit is increased by 1. So if it was 1.36, then we're going to round that up to 1.4. So in this example, what we're doing is we're rounding to 2 significant figures. We're starting with 3, so we've got our 1.33, which has 3 significant figures, going to round that to 1.3. 1.36, on the other hand, we're going to have to round that to 1.4. So this is simple rounding, so going from 3 significant figures down to 2. And I'm sure everyone is able to handle that. If not, you can discuss this in the tutorial. Don't be shy in tutorials and in lectures as well. You ask as many questions as you like to. These are very interactive. So these aren't the traditional style of lecture that you'll have at a university that has very large class sizes where you're supposed to stay quiet. You're allowed to pipe up and ask a question during our lectures. Or send me an email if you're having trouble. Not a problem at all. Let's have a look now at calculations involving errors. So this is something completely different. Okay, let's have a look at errors. Now, there's going to be an amount of error associated with a measurement. So, for example, let's look at what happened if we had a repeating measurement, and we're going to repeat that measurement several times. Okay, so we're going to try and gain some confidence in the accuracy of our result because we're getting different values. So we keep repeating our measurement, and we're going to take an average or a mean. So what we're going to do is going to say we've taken 1, 2, 3, 4, 5, 6 measurements, okay, and we've got our 6 measurements, so 1, 3, 5, 6, 7, 8. Add those all together, divided by 6 gives us 5 for our mean, for our average. It's taking a simple average, okay. The median, on the other hand, is the value that lies in the middle of the results. Now, if you've got an even number of results, you're going to have to take the mean of the 2 numbers that are right in the slap bang in the middle, that are right there in the middle. So, because we've got 6 numbers in this series, we don't have a number that lies in the middle. If we did, that would be our median, but instead we've got 2 numbers, 5 and 6. Let's take the mean of those 2, and the median becomes 5.5. Alright, so if we have a look at the amount of error that we've got in our range, it's 5 plus or minus 4. So 5 plus 4 is 9, take 4 as 1. Our maximum amount of error that we're seeing is 4. So our error in that range is going to be 4. So 5 plus or minus 4 in that particular data set. What is standard deviation? So standard deviation is a measure of how spread out the data is. Okay, it's the most common way to express precision. And standard deviation can be defined as the square root of variance. Well, that's very useful, but what is variance? So variance, sometimes variance is denoted as standard deviation squared, or sigma squared, that's a sigma. Average of the squared differences from the mean, that's what it is. So average of the squared differences from the mean. So in the previous example, the mean was 5, okay? So let's find the differences from the mean, square them, and average them. And that's what's happening in this next operation here. So we know that the mean was 5, and we had our series being 1, 3, 5, 6, 7, 8. So we're going to take 1, subtract 5, and square it. Then we're going to take 3, subtract 5, and square it. We're going to take 5, subtract 5, and square it, and so on. Add those together, divide by 6, because we've got a total of 6 results, and we get our number, which is 5.67. This isn't the standard deviation, this is the variance. Now, because standard deviation is the square root of variance, let's go ahead and take our square root of variance. So our variance is 5.67, let's take the square root, and we get 2.38. So the answer would be 5 plus or minus 2.38. Okay, this is how we express our precision, okay, or our error, if you like. Right, we can round off to one significant figure. Why are we rounding off to one significant figure? Look at those values. Okay, we've just got one significant figure in each of our measurements. Our measurements originally were 1, 3, 5, 6, 7, 8. So we've got no decimal places there. We've only got one significant figure in each of those measurements. Let's round off to one significant figure, so we get 5 plus or minus 3. Okay. Now, let's look at a practical example. So let's say we're measuring the heights of an array of dogs, okay, different dogs. Now, we've got some different breeds of dog here. We're going to measure those to the shoulder. So you can see over on the left, we've got quite a large dog sitting on 600 millimeters high, and we've got quite a short dog there as well. So the shortest dog, I believe, is 170 millimeters. What we'll do first is take the mean. So you can see here we've taken the mean, and the mean is 394 millimeters high. Now, let's have a look at the variance. Now remember what the variance was? It was the difference from the mean squared. So what we've done here, now you can see we've almost skipped a step. We've gone ahead and we've taken 600 minus 394 gives us 206. I'm going to square that. Okay, then the next value here is 470 minus 394, then we're going to square that. That gives us 76 squared, and so on. We've done that for every measurement. Notice that some of them are negative numbers. So this is where we've got here 170 minus 394 gives us negative 224. We're going to square that. And if we add all of those together and divide by how many there are, so how many dogs were there? There were 5. So divide by 5, we get 21,704. Now this isn't the standard deviation, this is the variance. Now to get the standard deviation, we'll take the square root of that answer and we'll get 147. Now this is 0.32, but remember, significant figures, it's going to be 147. Now why didn't we go to just one significant figure? Because we're dividing by 5. Okay, so some numbers are exact numbers. We know that there's exactly 5 dogs. It's not a rough estimate. It's not, there's not really 5.1 dogs, but we're just rounding down to 5. There's exactly 5 dogs. So some numbers are exact, and we don't take those numbers into account when we're calculating the number of significant figures. So in this case, we really do have 3 significant figures. Okay, and it comes back to our measurements, and our measurements were taken to 3 significant figures, and they're in millimeters. All right. Now, what's the standard deviation tell us? It seems fairly arbitrary, but what do we actually use this number for in science? Well, this can tell us when data is unusually high or unusually low. Okay, so if you might be taking blood levels of a particular analyte from a population, and you need to know whether one of the patients or one of the persons has an unusual blood level of say a liver enzyme ALT. And so what you might look at is the standard deviation and see whether it's going to fall outside of that standard deviation. And in reality, I suppose a lot of you have probably heard that we do have reference ranges that we use when we're doing blood analysis. This is a similar concept, but now we're just simply using the standard deviation instead for this particular data set, which is the height of dogs. And we can say that, for example, our Rottweiler is an unusually tall dog because it's above that standard deviation, which could be viewed as an acceptable amount of error. Okay, and your Dachshund's an unusually short dog because it's falling below the blue line there as well. So this is what we might use standard deviation for. Right, so in our calculations, we're going to have to be able to work with errors as well. So when we're taking a measurement in the lab, now we need to know that these measurements are going to be associated with an amount of error, and this is due to the limitations of the glassware, okay, that we're working with. So any quality glassware that we're using, now you might find that in the lab we actually have a mixture of different brands of glassware, and you might find that some glassware has the error written on it, inscribed on it, and others doesn't. Okay, and if it doesn't, we have to estimate the error. Okay, and when we're estimating, we'll go ahead and use half of the smallest distance. So if the smallest distance on our burette is 0.1 milliliters, we'll consider 0.05 milliliters to be the error if it's not inscribed on the device that we're using. Now, errors propagate. obviously, if you've taken more than one measurement and you're going to use this for a calculation, your errors are going to snowball. They're going to get larger and larger because you're getting different errors from your different measurement devices. Okay, so in this case, what do we do? What do we do with the errors after they've magnified? So if we're adding or subtracting the numbers, there's different rules for that than when we're multiplying or dividing. So if you're adding or subtracting, what we do is, now you can see here we're using this symbol, this lowercase symbol here, that's called a delta. That's a lowercase delta. An uppercase delta just looks like a big triangle. And now it's our lowercase Greek symbol delta. So delta Q means the error in Q. Okay, so Q is our answer in this case. So Q is our measured value. Q is our answer after we've added together our different measured values. Okay, so we're adding together A plus B plus C, and we want to know the answer Q is what we're solving. Now the error, the overall error, is calculated by taking the error in A, squaring that, adding that to the error in B, squaring that, adding that to the error in C and squaring that, and taking the square root of the whole series. And then, you know, it doesn't matter if you've got 3 different measurements or 10, you do it the same way. So you square each of the errors, add them all together, and take the square root, and that is the overall error in a measurement Q. That's for adding and subtracting. If you're multiplying and dividing, we actually do this a different way. So for multiplying and dividing, we say, now you can see here in this example, you know, we might have 6 different measurements. Let's call them X, Y, and Z on the top, and A, B, and C here on the bottom. And it can be, you know, you might have a very large series. Okay, so it might be a very large series of measurements. Doesn't really matter. So the way that we calculate the error in Q is consider the error in Q divided by Q. So delta Q on Q equals delta A on A squared plus delta B on B squared plus delta C on C squared plus delta X on X squared. So the error in A divided by whatever the value of A originally was, and then square that. So if the value of A was 3 plus or minus 1, okay, then it would be 1 divided by 3 squared. So the error in A divided by whatever A was squared. Add that to the error in B divided by whatever B was squared, and so on. Then you take the square root of all of that. And then that doesn't give you the error in Q, which is your final answer. That gives you delta Q on Q. Now to solve for Q, you need to consider that you then must have to multiply by Q, because that's delta Q on Q. Then we have to go through and multiply by Q to get our error, our true error in Q. Okay. Now if you're multiplying by an exact number, it's a little bit different. So in this case, if Q were to equal AX, then our delta Q, or our error in Q, would be the absolute value of A, meaning you don't consider whether it's positive or negative. If it's negative, you convert it into a positive number. If it's a positive number, it can remain as a positive number, multiplied by the error in X. Okay, so if you're multiplying a value by an exact number, you can multiply the error by that same number if it's an exact number. Okay. Here's an example. Now, this is a bit of a tricky one because we're having a look now at the density of a particular solid. Now, imagine we've measured the volume of a solid. So volume is how much space something takes up. Okay, so I might just have to draw something here. Let's see, my pointer options. Okay, if I take a pen, is this going to work? Okay, let's see. If I take a pen, now imagine we've got a measuring cylinder. Now, I'm not the best artist, and I'm drawing with a mouse here, so let's see how this goes. Okay, well that's pretty good. All right, there's a measuring cylinder. So that can be a measuring cylinder, so there's a circle on top. Okay, so we can see it's actually a 3-dimensional shape. Right, there's a measuring cylinder. It's got markings up the side to show us how much liquid is in there. Now let's say, I wonder if I can change the color. I can. Let's say we've got some water in our measuring cylinder. Alright, here's our water, our measuring cylinder, and we're going to put into here an object. So let's take an object, let's take an object. So object can be a circular shape, so it's going to have some mass. I'll colour it in. Okay, there's our object. We're going to put that into our measuring cylinder, plop that in there. There it is. And what's going to happen when we put an object in our measuring cylinder is the water level. What's going to happen to the water level? It's going to rise, right? So if we've got our water, the water level is going to come up from where it was originally. Okay. So here's our water, and it's going to come up. And what we can do is we'll have a look at how far it's actually moved. You can look at the measurement, the markings on the side of the cylinder, and see exactly how far the water's risen. And this is how we can work out the volume of the solid. So the definition of density is that density is the mass divided by the volume. So in this case, it's grams per milliliter. So we're going to solve how many milliliters the object is in terms of volume. We can work out its mass by weighing it on a balance, then divide the mass by the volume. So you can see here, to work out the volume, so I'll just highlight for you this calculation here, 13.50 minus 10.40. You can see that there on the bottom. That's working out the volume, and there's going to be some error associated with that. Okay, but what we're doing in step one is we're doing the calculation and we're ignoring the errors completely. So if we do the calculation, so 23.08 divided by 3.1 gives us 7.44 grams per milliliter. That's the density of the object. So quite heavy. So quite heavy object this one is. So okay, but we don't have error. So we need to calculate the error to go along with that measurement. So we're going to use the rules to work out the error in the denominator, because that's a subtraction. So that 13.50 minus 10.40 is a subtraction. So what we'll do is we'll square both of the errors for each measurement. So we can see here that we've got 0.05 and 0.05 for these two. So we're going to go ahead and do 0.05 squared plus 0.05 squared, take the square root, and we're going to get delta V, which is our error in volume, V for volume, 0.07. Now, there's a division as well. You can see how 23.08 divided by 3.1. That's our division. And to work out the error associated with the division, delta D on D equals, now our error was 0.02. Now, so right here, 0.02 was our error in our mass. And then where's the 0.07 come from? It's right here. 0.07 was our error in our volume. So it's 0.02 divided by, so error in the mass divided by the mass. So 0.02 divided by 23.08 squared plus 0.07 divided by 3.1 squared. So 0.07 was the volume, 3.1 was the error in the volume, sorry. 0.07 was the error in the volume, 3.1 was the volume. Divide the error by the actual volume, square that. Take the square root, that's delta D on D. So to work out delta D, which is what we really want, we have to multiply by D. And remember, density was 7.44. So 7.44 multiplied by 0.023 equals 0.17. And there we have it. So the density is 7.44 plus or minus 0.17 grams per milliliter. If you're having trouble with this, ask in the tutorial class, okay? Or just rewatch the example and see how you go. Work through it. So moving along, here we're looking at now some basic Excel graphing skills. Now, I think most of you know how to use Microsoft Excel or some sort of graphing software, and this is not necessarily something that you'll have to do necessarily in this course, okay? But if you haven't done it before, do go ahead and practice, because this is going to be important later on as you go through, and in other courses as well where you're doing lab reports. So you take your two columns of data, for example, highlight the entire data, including 0 points, click on Insert, Scatter Graph, okay, and then from there you'll get your basic scatter graph, okay? And if you right click, you can add a line of best fit, you can add a trend line, and you can also display the equation on the chart. Now, if you haven't done this before, it's not something that you're necessarily going to have to do in this course, but there's plenty of information online that you'll find online, whether it's a video clip or something like this, that shows you how to do this step by step. It's actually quite easy to do. So this is something that you need to make sure that you're able to do. And you can add, for example, titles and heading information and so on. It's quite modifiable. All right, so moving along now to classification of matter. So remember that mass is the measure of the amount of matter in a substance or an object, measured in grams. Okay, and this is going back to our prefixes and our units conversion, so kilograms to grams, grams to milligrams, and you can see in each case we're dividing by 1,000 or multiplying by 1,000 to convert in between. Okay, so that's mass. That's what mass is. Mass is the amount of matter in an object or a substance, and it doesn't change. It doesn't matter whether you're on the moon, whether you're on Mars, or whether you're floating in space. The mass of an object won't change. The weight will change. So your weight is less on the moon than it is on Earth. So weight is actually measured in newtons, okay? And it's got the relationship where W equals mg. So weight, it's convenient to measure weight in kilograms sometimes when you're it's not a true measure of weight. It's not the correct term to be using. Okay, quite often we say, oh yes, we're measuring weight in kilograms, but that will only work at a certain gravitational force. Okay, so when we've got different gravitational forces, then this is going to change, and it's more correct to measure weight in newtons. So remember, mass is the amount of matter in an object, and it won't change regardless of gravitational force. Let's have a look at states of matter. So, for example, here we have a solid, a liquid, and a gas. Okay, so what is the fundamental differences between a solid, a liquid, and gas? And I know you all know this. You all instinctively know, is it solid, is it liquid, is it gas? But if you were describing it to a Martian who just has no clue of these concepts, now, a solid will hold its shape. It has a fixed volume. It won't take the shape of the container that it's in. So if we've got this blue cube and I place it into a container, it's not going to take the shape of the container at all. It's going to hold its shape and its volume remains fixed. Okay, so remember that example earlier where we were looking at measuring the volume of a solid by the displacement of a liquid. Its volume is going to stay the same. Now, a liquid will take the shape of the container. Okay, so if you pour some liquid into a container, it will take the same shape, but it won't necessarily fill the container. Okay, so you can have a glass that's half full of water. You can have a container that's partially full of liquid. It doesn't have to take up the entire volume, whereas a gas will. A gas will take the shape of the container, and it will also take up the entire volume of the container as well. Okay, so this is the differences between a solid, a liquid, and a gas. So we talk about gases as being compressible. They're able to change their volume. A liquid can't change its volume, and this is the fundamental principles behind hydraulics. Okay, because liquids can't be compressed, we can use them in hydraulic systems, and because liquids can't be compressed, this is the reason why we can't compress a whole load of water and take it out to the desert. It's non-compressible, okay, whereas gases are. We can transport large amounts of gases in small containers and then decompress them where we need them. Alright, so moving along now to physical and chemical properties. So physical properties are the inherent characteristics of matter, okay, where no change in chemical composition occurs. So, for example, its state is a physical property. So consider water. So water can be frozen in the form of ice. It can be a solid, okay? Water can be liquid, or water can be gas. We call it steam, but water can be in a gas form as well. So this is a physical property. You can cool a gas down and it will become a liquid again. Okay? You can cool a liquid down and it might become a solid. But it's still water in all three of these examples. It's not going to change its chemical composition. So state change is a physical change. Colour is a physical property. It might be related to chemical properties, but it's a physical property. Its feel is a physical property. Is it hard? Is it soft? Okay? So its melting point, its boiling point is a physical property. Heat conductivity is a physical property. Electrical conductivity. Ductility, so that's the ability of a substance to be drawn out into a wire. Malleability is the ability of a substance to be rolled into a sheet. Or the density, that's the amount of substance in a particular volume. Okay, so we've already had a look at density today. So it's, for example, grams per milliliter, so mass per unit volume. Now, physical properties won't change the chemical composition of the substance, whereas chemical properties discuss how the substance reacts, how it changes chemically. These are chemical properties. Okay, so a chemical property describes, more or less, a chemical reaction of some kind. So now let's have a look at density and temperature calculations. So density is mass per unit volume. Okay, we've already covered this earlier in the lecture. Density is mass divided by volume. Okay, so grams per milliliter, for example. Now, let's have a look at an example where if we were to calculate the density of a pure substance, given that 100 grams of the substance occupies a volume of 12.5 cubic centimeters. All right, so looking at this example, how would you approach this question? So something that we could do is go ahead and take, now what is it, grams per milliliter or grams per cubic centimeter? So we could go ahead and say we're going to do 100 grams, oops, very messy writing, divided by 12.5 centimeters cubed, and a centimeter cube is equivalent to a milliliter, so it's still going to be grams per milliliter. So 100 equals, very messy, 100 divided by 12.5, so that's going to give me 8, so we get 8 grams per, and you can either put grams per cubic centimeter or grams per milliliter. Both are acceptable answers. Okay, so calculate the density of a pure substance given that 100 grams of the substance occupies a volume of 12.5 centimeters cubed. 100 divided by 12.5 gives us 8 grams per milliliter, or 8 grams per cubic centimeter, however you like to express that. You do have to give the units though whenever you give an answer, of any kind. So temperature is a measure of how hot or cold something is relative to some standard. Okay, temperature and heat are two different concepts. So temperature and heat, they're not the same thing. Okay, it's measured using, for example, a thermometer, at which a change in physical state occurs and is independent of the sample size, and the units are Celsius and Kelvin. Okay, and there's also Fahrenheit as well, and there's a conversion factor. So 1.8 multiplied by your temperatures in degrees Celsius plus 32 will convert to Fahrenheit. We won't work in Fahrenheit in this course. Okay, we're just looking at either Celsius or Kelvin, but not Fahrenheit. All right, so you will have to be able to convert between Kelvin and degrees Celsius. Now, there's no such thing as degrees Kelvin. It has to be just simply Kelvin. In Celsius, it's degrees Celsius. So the Celsius scale, as most of you are probably aware, at 0 degrees Celsius, that's the freezing point of water. 100 degrees Celsius is the boiling point of water. Okay, it's an arbitrary scale. Kelvin's a bit different. So with Kelvin, 273.15 Kelvin is the freezing point of water, and 373.15 Kelvin is the boiling point of water. Now, there's 100 degrees difference in the Kelvin scale, and there's also 100 degrees different in the Celsius scale between the freezing point and the boiling point of water. So it's 100 degrees in both cases. What this tells us is that the difference in 1 degree Celsius is the same as the difference in 1 Kelvin. But this is not true for Fahrenheit. Fahrenheit has a different amount of temperature associated with a degree. Okay, so a change in 1 degree Fahrenheit is not the same as a change in 1 degree Celsius. It's a smaller division. And our conversion factor is very simple. If you want to know the temperature in Kelvin, you take your temperature in degrees Celsius and add 273.15 to that number. Very simple conversion. And you'll practice a few of these in the tutorial questions. Now let's have a look at physical and chemical changes. So physical changes are changes that occur without changing the composition. Okay, so for example, changes of state. So changing from ice to water to steam. We've already covered a bit of this in the lecture, okay? So we know that changing state is not going to change the chemical structure. But chemical changes are changes that produce new substances. So in this example, we might add some sodium, okay, to some chlorine to make some sodium chloride. That's making a new substance. Okay, there's going to be a chemical reaction forming, and we're going to get some hints that there's a chemical reaction taking place because there might be some heat produced, there might be a color change, there's going to be some clues that a chemical change has taken place. Quite often there are. And you've got a new substance or new substances being formed, and you can't go back to the original substance very easily. Let's have a look at some definitions of matter. So pure substances have uniform or the same chemical composition throughout and from sample to sample. So if something's pure, it's going to have the same chemical composition all the way through. So can you have a pure sample of sucrose, of table sugar? Yes, you can. You can have a pure sample of sucrose. Okay? It doesn't have to have the same atom or element all the way through to be pure. Can you have pure gold? Yes, you can. And in the case of gold, gold is actually an element as well. So an element is any substance that appears on the periodic table. So if you find it on the periodic table, it's an element. By definition, it's a substance that cannot be broken down into simpler substances even by a chemical reaction. So we can't break gold down into anything else. We can't turn lead into gold. Lead's an element. You can't change an element into another element very easily unless it's radioactive, but that's something you might discuss in another course later on. So a compound is a bit different. A compound is a substance that's composed of two or more elements combined in definite proportion. So for example, sucrose, our table sugar, is a compound. It's not an element. It doesn't appear on the periodic table, okay? It's made of elements that are connected together. Now, in fact, in covalent bonds, we'll discuss covalent bonds later on, but all you need to know for now is that it's connected together. It isn't easily broken down into other substances, but it can be broken down. It isn't necessarily easy to break down into simpler substances, but it can be. Sometimes it is easy to break down into smaller pieces, okay, which may include elements. So we could break our sucrose down into carbon and hydrogen and oxygen if we wanted to, okay? And this is what makes it a compound. So a mixture is a combination of two or more elements or compounds. So for example, you might say smooth peanut butter. Smooth peanut butter is a mixture because there's all sorts of stuff in there. It can't be pure, really. It can't be a pure substance. Okay? Or you could take a soft drink. where it contains sucrose, okay? And in turn, so our soft drink is a mixture, right? But our sucrose in the soft drink is a pure substance, but it's a compound. Our sucrose is a compound and it can be broken down into elements. Now, when you've got mixtures, which are a mixture of two or more elements or compounds, you can have a homogeneous mixture, which has the same composition throughout, so it's smooth all the way through, like smooth peanut butter, or you can have a heterogeneous mixture that does not have the same composition throughout. So like crunchy peanut butter, if you like to think of it that way. It's not the same all the way through. It's got some solid in there, it's got some softer, creamier portions. It's not the same all the way through. Another common example is something like soda water, like a carbonated water, where you've got liquid and you've got gas and you've mixed them together. It is a mixture, and in fact it's a heterogeneous mixture because there's two different states in the same mixture. Okay? Let's have a look at our hierarchy of matter. So start with matter. Ask yourself, does it have a variable composition? Everything you can see is matter. Okay, so everything's going to fall under the banner of matter. So variable composition, yes or no? If yes, it's a mixture. Okay, so it's not pure all the way through. If no, it's a pure substance. Now, looking over there on the left still, if it's a mixture, does it have visibly distinguishable parts? If yes, it is heterogeneous. Okay. Now down the bottom here we've got some examples. So an example of something heterogeneous might be a suspension. Not everything that's heterogeneous is a suspension. Okay. This is just an example. What's a suspension? A suspension is an example of something that you might buy that you need to shake before use. So maybe orange juice, where the pulp settles to the bottom, that's a suspension because you give it a shake and it's going to redisperse. Okay, and it's going to remain that way for a significant amount of time so that you can use the product. That's what a suspension is. But not every suspension is heterogeneous. Not everything that's heterogeneous is a mixture. If your mixture has visibly distinguishable parts, it's heterogeneous. If it doesn't, it's homogeneous. It's smooth all the way through. So for example, a solution. Okay, it doesn't have to be a liquid, doesn't have to be a cream, it might be a solid. It can be homogeneous. You might have some homogeneous brass. Some brass metal might be a mixture, but it's same all the way through. It's not going to have air pockets. It's not going to have hard bits and soft bits. It's the same all the way through. Let's have a look at pure substances. Do they contain various types of atoms? If no, then it's an element. Okay, if yes, then it's a compound, if you've got different types of atoms in there. So for example, our sucrose that has carbon and hydrogen and oxygen is a compound. Alright, let's move along. You can separate mixtures. Okay, so you can take a mixture of sugar and water and you can separate that, perhaps using a distillation. Okay, or you might have a mixture of, say, a solid and a liquid, and you're going to filter it. So distillation and filtration are two methods that you might use for separation of a mixture. Here's a quick quiz. So we need to match each description below with the following microscopic pictures. Okay, note that more than one picture may fit each description. So A is a gaseous compound, B is a mixture of two gaseous elements, C is a solid element, and D is a mixture of gaseous element and a gaseous compound. So have a think about this. You can pause the video, have a think, and see how you go. Okay, so number 2 was a gaseous compound. Number 4 was B, a mixture of two gaseous elements. C was 3, a solid element. D was number 1, a mixture of a gaseous element and a gaseous compound. That brings us to the end of the lecture. Now, here's some support material. Now, you don't have to necessarily complete all of these questions. In fact, I don't set homework in this course. What I do recommend you do is make sure that you practice all of the tutorial questions every week. Okay, and if you want some extra study, go ahead and open your textbook and have a look in there, and there's plenty of questions in there to have a look at as well. And if you do both of these things, quite often you will get a very good mark for the course. So I'll leave it there. Thank you very much for your attention, and I'll see you next time.